I think that the idea of this conference is a very important idea, because I believe that one of the difficulties that our science faces is that it has become too large and it looks fragmented. And it's clear that, for example, when we come to these talks, that some people are very comfortable with everything that's said, and other people have difficulty following even very basic stuff in a different area. So I think that it's very important that we try to understand what we are doing, because I do believe that a lot of what we are studying and what we are interested in is really very closely related, and the ideas can be carried over. So I would like to walk today along the line between discrete and continuous mathematics and sort of point out some of the sites for you. I won't be able to cover everything that I, even in a minimal tour, would. So you will see some things announced here on these slides, which you will be able only to find in the final paper. So let me start with saying that discrete and continuous mathematics are they have rather different features. First of all, they are rather separate cultures. I mean, there are people who understand discrete mathematics and people who understand continuous mathematics, and they are pretty much clusters. And also, basic methods are different. In discrete math, you use induction. In continuous mathematics, you use derivative. I mean, sort of. But on the other hand, I would like to, one thing I would like to point out is that I think that in many application areas, it is the interaction of discrete and continuous that makes the problems difficult. And therefore, it's particularly important for us to understand how this interaction works. So for example, take protein folding. A protein is described by a completely discrete object. It's a sequence of, I don't know, 2,000 amino acids. And some are maybe.
Absolutely exceptional. 200, very similar to 300.
It goes from 50 to 5,350.
Thank you. So it varies very much. There are huge protein molecules and small protein molecules.
My majority of them is expectation and
well, whatever the numbers are, is a discrete object, which is.
The basis you can try to have right numbers. You cannot say just take this number without being responsible for it. Completely distort the picture. 200, 2,000, different world.
It's finite. It's finite.
Well, actually, there are proteins which are 2,000, maybe even 5,000. Thank you. Right. So this is a completely discrete object, and the crucial issue is how it coils up in free space, which involves a lot of continuous mathematics, like all the quantum mechanics that goes into describing how these particles interact and how they determine the final shape, which in turn determines whether it will be a snake venom or some kind of enzyme that's very useful for you. So anyway, let me try to start my walk. And that's a first remark, and I won't elaborate too much on this. And of course, you can always say that there are lots of uses of discrete ideas. Just this, it's a random collection of a few, like the definition of the Riemann integral, or you triangulate a manifold to define some kind of homology groups, or if you want to numerically solve a differential equation, you use a grid and it's some kind of discrete procedure. And so you use finite as approximation of the infinite or the continuous. Also, a little bit more subtle idea is that infinite is often an approximation of the large finite. And in some cases, that can be made completely exact, like compactness theorems. If you know something for the infinite, for example, it's easier to prove Ramsey's theorem for the infinite, but by some general principle called compactness, it implies the finite version. And then, of course, often you use heuristics from the continuous to prove discrete theorems or to understand what's going on. But so this is sort of a let me go to some next level where actually results from one side are essentially used to obtain results on the other side. And I thought of giving you two examples, and I will actually only describe the first one. You can pick a continuous result, and then sometimes it has a very elegant, simple proof using some non-trivial result from discrete mathematics. Or more often, there are more examples of the other side where you prove some completely discrete result using continuous ideas. So let me describe you a construction of the Haar measure using the marriage theorem in discrete mathematics. This was indicated, but not quite worked out in a paper of Harper and Rota. They do a similar construction, but let me do the Haar measure because that's what's the nicest. So actually, what I will do is to show that if you have a compact topological group, then you can define an invariant integration. So you can define a linear functional and continuous real-valued functions, which is, well, it's linear. Sorry? Sorry?
He wants to know why you're not doing locally.
The compact case is totally trivial. I mean, I think Henri Cartan wrote a confounded note in which he put convergence, the best thing. I mean, it's nothing.
Yes.
It's a difficult case in locally.
I know, yeah. I want to stay simple. You can do it locally compact, but it will become much more complicated, of course. But I just want to, I mean, I'm not claiming that this is a big result. What I would like to show you is that there is an argument which is very natural, and at some point there is a discrete theorem which really carries the weight. So let me try to describe you. So it's normalized, and it's translation invariant from both sides. And of course, the idea is that we would like to define the integral of f as an average of values of f approximated where A is a sort of uniformly dense finite subset of G. Now, what does it mean it's uniformly dense? Well, here is the definition. Pick a small open non-empty subset of G, and then say call it U, and define a U-net as a finite subset A, which intersects every translate of U. Of course, this exists. And a minimum U-net is a U-net with minimum cardinality. So it's the smallest possible U-net. So that's the definition of uniformly dense. Now, I still have to tell you what small means. And so here is the definition of small. Call two group elements close if there is a translate of U which contains both of them. And then it's just the maximum variation of the function. And call delta U as the maximum variation of a function over a closed pair. In other words, it's the maximum variation on on translates of u. And so small means that this delta u should be small. And again, it's trivial that such a u can be chosen. So, so this is the idea. And now here is, I want to get to the discrete situation. Yeah, I should put it there. Thank you. So I want to get to the discrete situation, or discrete result. And so the main fact is that this definition makes sense. In other words, if I average over one minimum unit and over another minimum unit, then the difference will be small. So if I prove this, then basically that's the end. That's where I will stop. Because from then on, you have the definition. And the rest is very routine. So, but here is the difficulty, because I know very little about these sets A and B. And I know that they have the same cardinality, but that's about all I know about them. So the idea is to show, so suppose this red point is one of these sets, and the blue points are the other. And the idea is to show that you can match them up so that each pair is contained in a translated copy of U. If you can do that, then it's obvious that replacing each red by blue changes the function value by at most delta, so the average changes by at most delta. Now, now that's a situation which looks pretty complicated because, again, we know very little about these two sets. So how to match them up? And, some obvious solution, there's no obvious solution, but luckily there is a theorem which tells you when these two sets can be matched up. Now, it's called the marriage theorem. It goes back to Frobenius, was this form probably formulated by Koenig. It says that what you have to do is to look at a set X of red points. So that's one of these minimum unit. And you look at the neighbors of it. And you count the neighbors. And if the number of neighbors is at least as large as the set, and that holds for every X, then there is a matching. So I would like to argue that this is the case. So let me look at any set X, and here are the neighbors of that set X. And suppose that the neighbors are smaller, the neighbor set is smaller, and then let me look at the neighbors together with the rest of the red points, and I claim that this is a unit. Why is it a unit? Well, suppose it's not a unit and there is a translate of U which it doesn't meet, but it picks up a red point because the red is a unit, so it contains a red point. It must contain it from X. And it also contains a blue point, but not from this set, so it must be outside this. But then there must be that these are close, and in other words, this point is a neighbor of X. So this contradiction shows that this is a unit, but it's smaller than, say, this red set, which is impossible. So it's really just trivial to verify that the condition holds. It's just a recasting of the definition. And from this, we now conclude that this main fact is indeed true. And as I told you, I won't go on. From here, it's really routine to complete it. OK, now, there are actually several other examples of the application.
Well,
yes?
You don't need perfect matching theorem. You want a weighted version of these measures. So you just duality.
You could replace it with linear programming duality.
Because you force stronger theorem which you don't use. Yeah?
Exactly.
The weighted theorem is not
in fact, the proof that people used to have before is you just take any limit of this and you prove it's A measure. But because you have uniqueness of our measure, you know that you have convergence for no price. You don't have to make any proof.
No, but I was saying this case, yes,
Well, I wanted to show that this that matching theory does indeed come in, and I wanted to add a story to this. I had a friend who works in topological measurable spaces, and that was a long time ago. He came to me and said, well, I have a problem and you might be able to help me with. And he told me a question about measures that is actually could be solved in exactly along the same lines. And so I was thinking about it, and then I said, okay, I see now why you came to me, because this is really like a measure theoretic version of the Koenig's theorem. In that case, actually, the weighted version was not enough. And then he said, well, no, that's not why I came to you, but I know that you wrote your master, I wrote my master's thesis about topology, and he thought that I might know some kind of embedding theorem which would help him to reduce it from a complicated topological space to a discrete, to something like a cube. So the point is that in some cases there are combinatorial complications, and it may help you that if you know that some certain combinatorial complications can actually be handled using combinatorial theorems. And this, I just picked sort of the simplest version of this idea to illustrate this. So let me go on and go one step further. And as a little bit more interesting level of interaction is where I know at least, there are many fields in discrete mathematics. You could even argue that in a large part of discrete mathematics, progress comes by trying to apply more and more involved techniques from continuous mathematics. And, or at least very substantial progress comes. And I will only give a verbal description of this line, where we go from, we start with discrete optimization. So what's discrete optimization? It's where you try to find an optimum out of a finite set, like the traveling salesman problem. Now, it is clear that in this case, you cannot really apply anything like take gradients or subgradients and so on, because we only have a finite set. The problem, you might even argue, is trivial, except that we know that the traveling salesman problem is non-trivial because that finite set is huge. If you have 1,000 or 2,000 cities, then it's like the factorial of this is the number of solutions. So it's more than astronomical. And by the way, people do solve traveling salesman problems with a couple of thousand cities pretty routinely. So there are methods. And so the methods, there are combinatorial methods for various discrete optimization problems, but the standard idea is to try to turn it into a linear programming problem. Now, linear programming is the area which lives on the boundary of these two things, because if you, in one way, it's rather discrete because it can be described by a finite number of linear inequalities, but it's continuous after all. It talks about real solutions of that system of linear inequalities. So this basic idea of reducing discrete optimization to linear programming was worked out in the 60s and 70s and by Fulkerson, Edmonds, and others, Hoffman. And the idea is that you first write a discrete optimization problem as a linear program with the side constraint that the variables have to be 0, 1. And that's not difficult to do, because the 0, 1 corresponds to logical decisions, like do I put this edge into the traveling salesman I'm looking for or not. So, and then the conditions can be translated into linear inequalities involving these 0, 1 variables. And then what you can do is to go to the linear program, which means you forget about the condition that these variables are 0, 1. You get a linear program. You solve that linear program. And then there are various ways of, of course, the solution of the linear program will not be what you want. It will be typically some real values instead of logical values. But then there are all sorts of tricks to go back and obtain either exact or approximate solution of the original discrete program. And indeed, as I told you, this technique allows people to solve traveling salesman problems with 2,000 cities, 2,000 factorial possibilities, and you are able to pick the optimal one. And it's an exact solution. There's no cheating going on. It's a provably find the optimum solution. Now, there is an interesting next step, which I would like to mention because it contains some of the buzzwords that have come up here, like lift and project yesterday in Eli's talk. And so it's something that I think might be interesting to look at. And this is, I will only be able to give you a two lines of the idea, and then hope to be able to elaborate in the paper better. So the idea is that instead of saying that xi is 0, 1, let's say that xi squared is equal to xi. Well, that is neat, but it doesn't help. It reduces this condition to some algebraic conditions, but it doesn't really do any good. The next idea is to linearize, which is, of course, very standard in algebraic geometry and so on. So what you do is you introduce the variables xi, xj, the mutual product, as new variables. And you in fact, put them together in a matrix Y. And then it's easy to see that any linear inequalities that hold for the xi's are inherited for this matrix. But in addition, we know that this matrix is positive, semi-definite, and has rank 1. In fact, under these conditions, the problem of optimizing over these matrices is exactly equivalent to the original, because once it's positive, semi-definite, and has rank 1, it can be written like this. But the idea is, out of these two properties, the positive semi-definiteness is nice because it's convex. And rank 1 is nasty. So we forget about rank 1, and we just keep positive semi-definiteness. And this way we get a relaxation of the problem. It's not exactly the same problem, but it turns out that if you solve it, then quite often you get the right value, your right solution, or you get a good approximation of the right solution, and so on. There are several nice examples, but I won't be able to go through them. Let me just remark here that progress through continuous mathematics is even more in this than just convexity. Because if you try to optimize a convex function, then of course there are very, very nice methods using, I don't know, steepest descent, conjugate gradient, and even more sophisticated methods of continuous mathematics. The point is, however, that if you have non-differentiability, then you run into troubles. And unfortunately, the positive semi-definite cone is convex, but neither polyhedral nor differentiable. It has edges, but it also has surfaces. So the standard methods of linear programming don't extend because it's not a polyhedron, but also this kind of conjugate gradient methods don't extend. And actually, semi-definite optimization as a practical method was stuck on this problem for about 15 years, until about 5 years ago, maybe 10 now, Elizadeh discovered that you can actually apply very nicely interior point methods. Now, interior point methods mean that you don't optimize the function, but you sort of go to the minimum through the interior through a rather tricky analytic method, path-following method. And in this case, it turns out that if it's basically the log of the determinant that you want to minimize instead of the function itself. So anyway, the point is that through this rather complicated analytic tool, or somewhat complicated analytic tool, this problem became much more efficiently solvable, and it's now a very, very fashionable and much studied area of optimization. So somehow the idea is, and there will be more, I just picked discrete optimization, but there will be more, there are more, topology is used, and so there are several areas where you try to introduce more and more of the techniques of continuous mathematics to solve problems which are discrete by nature. Now, let me very briefly mention it's number 4, that there actually is an area of mathematics which can be thought of as actually studying this borderline between discrete and continuous mathematics. It's called discrepancies theory. And let me just, it would be a beautiful topic to talk about. It's very nice, very deep results. But let me just mention a classical result in this area just so that you know what I'm talking about. So suppose you have a continuous measure, say the uniform measure on the unit square, and suppose you want to approximate it by a discrete measure, which is just uniform measure on n discrete points. Now, how well can you approximate it? And and suppose that we are interested in the area of axis parallel rectangles, and if T is such a rectangle, suppose the area of it is A, then if you have n points, n discrete points, then the number of these discrete points, which is the discrete measure up to scaling of T, you expect it to be approximately the area times n. But this cannot be exact, of course, because there are different measures. So the question is, how far do these two measures have to be? And there is a very, I think it's a very deep theorem of Schmidt, which says that the best discrepancy is log n, so that no matter how you pick the n points, there will always be a rectangle where you find a discrepancy of log n. And that's best possible, which is, again, not quite trivial, but somewhat easier to show by various constructions. So this is only one example of many similar questions which ask how well can you approximate continuous measures and other objects. It's a unit rectangle. Or the rectangle? Yeah. So you take the, well, for all rectangles, so you take all rectangles, and over all rectangles, you look at the maximum difference between these two. Sorry?
How big is the rectangle for which the discrepancy is log n?
It's the maximum over all rectangles.
In the proof, he's asking, is there a typical size of rectangle in the proof of the theorem where you
I don't think so.
Some average.
No, it's not. I think. Well, I don't know if there is a typical size. Probably not. You can have small rectangles and big rectangles, which are bad. Of course, not very small. I mean, they have to be at least log n over n. Otherwise, they are. And of course, constant size rectangles are easy to satisfy, so it will be somewhere in between. Okay, again, this is something which would be nice to talk more about, but I would like to come now to number 5, which is I would like to claim that there are actually many phenomena in mathematics, and this is just a random collection, where you have continuous objects and discrete objects, or you have continuous and discrete version of the same question. And so, for example, sequences and analytic functions, and somebody, I think, mentioned this yesterday, that you have a recurrence and how interesting it is that it translates to a differential equation and vice versa. Or results about the asymptotic behavior of a sequence translates into results about the singularities of the generating function and so on. This is all very old classical stuff. I'll come back to the Laplacian in a minute, and we'll talk more about it in the rest of my talk. This, of course, can be defined on manifolds, standard ways, and can also be defined on graphs. And I would like to talk about this more. Let me mention another such thing is iteration, where simple steps lead to complex structures. And that's, of course, the main topic, or one main topic in dynamical systems. Iteration comes up, of course, in any algorithm, including numerical analysis, which I put in that line. But, of course, it also comes up in discrete mathematics. For example, you could use this complexity that you introduce by iteration to generate pseudo-random numbers or something like that. It's a very, I think this question should deserve a lot more study. I mean, any algorithm is iteration, and there is, it's not as well understood whether there are similar ideas in both areas. And then, of course, there are lots of other areas in mathematics where discrete and continuous mix, and probably difficult to separate. But so I would like to talk about this, the Laplacian. So the Laplacian, what could be more continuous than a differential operator? But we can define a Laplacian, something called a Laplacian for any graph. And for simplicity, I restrict myself to regular graphs of degree d. So I'm talking about graphs which are finite graphs. They have n nodes, and always denote the number of nodes. And every node has degree d. And aij denotes the number of edges between I and j. Typically, this is either 0 or 1, but it could be some other number. And so each row sum here is 0, because these numbers add up to the degree of 0.1, which is put in the diagonal. So that's the Laplacian of the graph. And the first question is, why is it called Laplacian? And of course, well, one explanation is that if you think of the graph of a lattice, just a standard lattice, and you connect 2 points if they are closest to each other, and then you look at a discrete approximation of this Laplacian, you get something like that. You will get the middle point, say in the plane, 4 times minus the sum of the neighbors, and that's exactly what this thing does here. Now, well, we heard a lot about all sorts of uses of Laplacian all over the place. Let me mention a few graph theoretic aspects of the Laplacian. Maybe I should leave this here. Of course, one likes to look at the spectrum of the Laplacian. The smallest eigenvalue is 0 because each row sum is 0. And actually, I prefer to scale it by 1 over d. But that's not very relevant. And so the other eigenvalues are lambda 1, lambda 2, lambda 3. And so, yeah, I assume it's a connected graph. Thank you. Thank you. I forgot to mention that. Yeah. Then there is a non-trivial gap below below lambda 2, And for example, there is a very basic result by Alon and Millman in one direction and Alon in the other, which is sort of a discrete Cheeger inequality, relates this gap to the expansion ratio of the graph. There's a very tight connection. I'll come back to some version of this later, so I won't explain it. Let me just mention that it turns out that you can extend a lot of things to graphs. Harmonic functions can be defined in a natural way. The heat kernel can be defined. Green's formula can be proved, and so on. So there are. It's already a little bit surprising that it seems that for a graph, if we want to think of a graph, any general graph, as a kind of generalization of a manifold, you lose all structure. I mean, there is no. In general, it's not even true that locally, say, the degree would be the same. Even that's not necessary, even though I assume that. But we don't assume any structure of this graph. And yet, the Laplacian can be defined, and it has already several non-trivial theorems can be extended. So let me try to talk about what got mainly interested in these issues, and that's because of the problem of sampling. So let me mention here that one of the progresses in computer science has been that various types of basic algorithmic questions have been identified. The definition of the class NP, which was mentioned here, involves a very basic algorithmic question. You try to find something which, if you find it, then you know that's what you were looking for. So it's easy to verify that once you find it, that's what you want. There is another class called Sharpie, which is counting problems. And again, it was an important step forward when it was identified that this can be formulated precisely what a counting problem is. And then you could prove relationships between those problems. Now, sampling is also a very basic question. You have some large set. Typically, again, we assume that if you find an element, then you know that this element is in the set. So that's easy to check. And then you want to generate a uniformly random element of this set. So that's a very fundamental algorithmic problem. And well, this is just some kind of mention that applications of this are all over the place, from numerical analysis to physics to card shuffling, which is probably the most classical special case of sampling problems. So you want to sample from the 52 factorial possible arrangements of your deck of cards. Now, at this point, I'm doing a little injustice to this problem because I'll only talk about one approach to sampling, which is using Markov chains. That seems to be among the general sampling algorithms the most useful. And so here is a sketch of this approach. So the idea is that you define an ergodic Markov chain. We can think of it as defining a regular graph, and then you do a random walk on this graph. This is the same thing. Well, the state space is this S from which you want to sample.
Why it's regular?
You need a regular graph because I restricted myself to uniform sampling. If in general, you would be sampling proportional to the degrees. So if the graph is not regular, but that's not a serious condition. You can always make a graph regular by adding loops at points, and that won't change things too much. So, so you define such a random. So if you make it regular, then the stationary distribution will be uniform. And you want to set it up in such a way that one step should be easy to implement. I mean, you could think of a complete graph, then one step will take you to a random point, but that's not easy to implement. So you want to shuffle cards, well, you need some kind of trick to do one move in the shuffling. But card shuffling is an example of this. You set up such a graph, and then you do random walk on it. Now that part is usually easy. There's usually some natural or at least not terribly complicated way of setting up this Markov chain. And now if you stop after a sufficiently large number of steps, then you will be approximately uniform. Now the question is, how is this sufficiently large? And the first step, one would think that you have to do this maybe as long as the number of nodes in the graph or something like that, because you want to get everywhere after all. But actually it's much, much less. There is, for example, for card shuffling, there's a famous theorem of Bayer and Diaconis which says that 7 shuffle moves suffice. Now there's this big graph of 52 factorial nodes, and you start anywhere, and after 7 moves, you're uniform all over the graph. So it's a wonderful...
and 6 is not enough.
And 6 is not enough, yeah. 6 is not enough. So the point is that you would like to know how large sufficiently large is, and that's, of course, necessary because you have to tell the algorithm when to stop, and that's a very difficult question in general, and has a lot to do with the Laplacian. And that I call this the mixing time without exactly defining what the mixing time is, because we would get into troubles of how you measure convergence and so on. So let me just somewhat informally say that mixing time is the number of steps you need in order to get close to the stationary distribution. It turns out that it's a pretty robust number, so various versions are not very far apart. So if you start with a distribution sigma, then the distribution sigma t after t steps can be obtained. It's just simple linear algebra. You take the adjacency matrix of the graph and scale it down by the degree. The tth power of that applied to sigma gives you the distribution after t steps. You can write this as I minus 1 over d times the Laplacian to the t, if you wish. And from this, from this or from other ways, you can also get the recurrence that sigma t plus 1 minus sigma t is the Laplacian applied to sigma t. And you can recognize this as a discrete heat equation. It's a discrete time heat equation. And indeed, in this whole theory of mixing time, the heat equation plays a very important role. All sorts of methods from heat equations, Harnack inequalities, Lach-Harnack inequalities, and a number of these can be applied to obtain, can be extended to the general case. And that's really the miraculous thing here, that it turns out that all these don't have anything to do with the manifold structure that underlies it. It's all just properties of a dispersion on a graph, basically.
Manifold, you never use manifold structures. I mean, this kind of mathematics, you never use manifold structures. You use the theory.
Yeah, that's what I'm saying. Yeah.
Actually, much of this was done to us in discrete case by Kessler, yeah?
Yeah. Yeah, I mean,
It's not miraculous.
Okay, right. Okay, it's not miraculous, but I was trying to make more salesmanship here than necessary, but I certainly found it interesting. And let me tell you that it's not always trivial to do these extensions if you look at the proofs in the continuous case. I mean, there are proofs in the continuous case which use tools that do not extend to this, at least not in a straightforward way. So using this, you can see that the mixing time is about 1 over lambda 2. You can also define some other version of the mixing time, but that's very close to this. Probably the ratio is bounded by logarithmic by the logarithm of the number of nodes as the maximum. That's an L1 norm. Should be 1 here. No, whatever. So it's the maximum L1 norm of a function where the L infinity norm of the Laplacian is 1 and the minimum of the function is 0. So it's a very simple property of the Laplacian that determines the mixing, governs the mixing time. Now, that's fine, but unfortunately, if you think of some of the applications, then the Laplacian is not easy to, it's not easy to find the eigenvalues of the Laplacian. It's easy to find if there is some algebraic structure, you are working in a group, or there is some kind of symmetry involved. Then usually it's easy. But in the general case, when you can think of just a graph, say, whose vertices are all the matchings in a graph, and an edge means that you get one matching to the other by switching one edge over, that kind of situation is impossible to compute the eigenvalues of the Laplacian. And the graphs are huge. You know, think of 52 factorial for the simple problem of card shuffling. You can think of much, much larger graphs. I mean, think of the example of statistical mechanics, where you would like to generate a random sample of ups and downs for each molecule in a grid, in a large grid. So there already the size of the graph can be much, much larger. I mean, it's unbelievably large. So you cannot really try to compute these eigenvalues directly. And there is a standard procedure which, to estimate the mixing time, reduce it to isoperimetric inequalities. And then you have to prove these isoperimetric inequalities. And in analysis, you prove the isoperimetric inequalities by using flow theory. And that's, again, a mixture of continuous and discrete mathematical ideas. Let me give you an example which is not really the best example in the sense that, so the problem is, given a convex body K in Rn, you want to generate a uniformly distributed random point in K.
It's presented in what form?
Say that the convex body is presented as a system of linear inequalities, in which case it's a but in fact, the example is valid for any presentation of the convex body which satisfies a minimal requirement. You give me a point, I should be able to tell whether that point is in the body or not. If I have any procedure to do that, then what I'm going to tell is valid. So here is one of the possible, there are several possible Markov chains that you can define that will do the job. One of them is called the ball walk. That's probably the most natural. It says that if you are at a particular point, you pick a small ball about that point and you move to a random point, uniformly distributed random point of that ball. And that's not difficult to construct. And one more remark has to be added, that if your step should take you outside the convex body, then you don't do that step. You stay where you were. It's not difficult to see that the stationary distribution is uniform, and the mixing time of this ball, of this walk, can be shown to be of the order n times d squared over delta squared. D is the diameter. Oh, I forgot to write it. So d is the diameter of the convex body, and delta is the step length. Now, that's not an easy theorem to prove. Let me mention here that this, of course, you may ask, why don't we take delta very large? I mean, the larger delta, the better off we are. Well, because in this mixing time, I mean, there are these problems here. If you are wasting too many steps, I mean, if you choose delta to be huge, larger than the diameter, then in one step you get a uniform point. But to make this step, you have to make possibly an astronomical number of trials. So you have to balance these two things. And in fact, if you choose everything properly, then this will be order n cubed, where n is the dimension. So it's not a terribly large algorithm. Let me stop here for a second and mention here that the first version of this algorithm was given by Dyer, Fries, and Cannon 10 years ago. And that was the first polynomial time algorithm for sampling and as an application for computing the volume of such bodies, which is probably the main application of this particular method. And the Dyer, Fries, Cannon procedure was actually order n to the 23. So it had a huge exponent. And it was actually sort of brought up as an example that polynomiality is not the right measure for complexity because, after all, there's no way to implement an n to the 27 algorithm. But the point was that once you have polynomiality, it shows that you understand something from the structure of the problem. At least one possible avenue for the solution you understand. And in fact, eventually it came down to something which is pretty decent, n cubed. And there is some possibility to bring it even further down. I mean, there's still work being done. But n cubed is not that horrible. It's still not very pleasant.
This kind of idea.
It was, the basic idea was Markov chains, but it was a different walk, and the several ideas were not there yet.
You just stated the result that in large dimension you can approximate the volume of a complex body in polynomial time.
In polynomial time.
Approximate means?
Approximate means that you give me an epsilon, and I'll give you a number, return a number, which is a random number, which will be within a factor of 1 plus minus epsilon to the true volume with large probability. And that can be done in order n to the 5th time. Let me mention here, and I think I'll have to stop then, that there is a negative result here which says that if you want to do it deterministically, then there is always at least a relative error of n to the n. So huge error as a function of the dimension for every deterministic algorithm. But if you allow randomization, then you can do it within a factor of 1 plus epsilon. So that's an example where randomization really helps. Now, let me point out that that does not contradict Avi's statement that probably randomization does not help because it's a different model. So it's, if you look at the details, it's a little bit different model. No, thank you very much.
So I think we'll try one question and the rest for the discussion. Any questions?
Here's a question.
Why is it a different model?
Because here I assume that the convex body is given by an oracle. That's what I said, that it's enough. I just assume that there's a black box which tells me whether a point is in the convex body or not. And that's only needed here to check whether I stepped out or not. And in such an oracle situation, you can usually prove lower negative results easier. There's more flexibility, so you can sort of play the oracle as kind of an adversary. There's a technique to prove.
Take this as some indication that you should be more suspicious.
It's just the special case that Lassi described in which the body is given by a system of linear inequalities. There is no such lower bound of n to the n of the error, but there is no lower bound, period.
But this oracle thing,
If you are allowed to look at the bits of the presentation, then maybe you can do
Use
some
that.
very efficient thing.
Okay, so we meet